Okay, today is the last part of the chapter 6 energy work power. We will focus on power. Okay, the definition for power. Okay, work done or energy conversion, the rate of work done conversion. The formula that we have is energy divided by the time. Okay, the SI unit for power is in watts. Okay, is in watts. Okay, work done or energy is SI unit in joules, and the time taken will be in seconds. Okay, primarily we have power to actually to make a more justified comparisons. For example, if I have two objects or I have two person, one person spend okay 40 joules okay doing certain work, then object B or person B, he also spend 40 joules to do the same work. So if you look at the amount of energy spent, we can't really say that object A, boy A, is as good or as efficient as boy B, even though they spend the same amount of energy, because we have not dealt with the duration. How long does boy A or boy 1 take to complete that particular task, or how long does boy 2 take to complete the task? So if boy 1 takes 40 seconds to complete the task and boy 2 takes only 10 seconds to complete the task, okay, when you look at these two factors together, energy and the time taken, we can actually make a more decent or more justified comparison about who is more efficient and who is less efficient. Okay, for example, you spend 40 seconds and you spend 40 joules, and you 10 seconds you spend 10 seconds you spend 40 joules, you can see that boy 2 is actually much more efficient as compared to boy 1. Okay, because why? Because we actually look at a more justified or more balanced comparison of just the energy followed by the amount of time taken spent to complete the task. So that's why we have this particular formulas of particular section dealing with energy and time. Primarily, both of them we have a name for it, which is called power. And this is the rationale. Like we take power, we look at power. Okay, SI unit is watts, like I mentioned. Okay. Now, a common example that we have, a simple one, the engine has 60 kilojoules, or 60,000 joules, and he spent his time spent is 10 minutes. Okay, simple formula. This is the formula stated in front. Okay, nothing fanciful. Okay, things to take note, like I mentioned before, the SI unit for power is in watts. Okay, so which means the component mass, the relative component mass also be in SI unit, which means the work done, the energy used has to be in joules, and the time spent has to be in seconds. So that's why for 10 minutes, okay, we will need to take one more step to convert this to seconds before we actually use the formula energy work done equal to time, work done divided by time to find power. Okay, so that's why we have these extra steps to convert the time to seconds. Okay, so this is one of the main hurdle that prevent or that stop students from using the formula effectively. Okay, one thing to take note is when we look at power, we have this formula energy divided by time or work done divided by time. Primarily, the common thing that we're looking at for is example, if I want to know the useful power, okay, the energy spent here, okay, will have to be the useful energy, okay, divided by time spent in doing the task. Okay, so then you can get the power for the useful power. If I'm looking at the rate at which heat is being lost, okay, the rate has been the energy is being lost. Okay, the formula is still the same, energy divided by time. I will find that the energy I'm dealing with here will be energy loss divided by the time taken in consideration. Okay, similarly, it's like the numerator is energy of work done. So which particular formula should I be using? Work done, energy, is that formula for energy? Okay, the correct answer that we're looking at for is the necessary energy. For example, if the energy I'm dealing with is I can actually consider it, I can actually calculate it using the formula of kinetic energy, then I will use kinetic energy formula in my useful energy. If I use the formula half mv square, okay, sometimes useful energy can be in the form of gravitational potential energy, okay, which is EP for short, which means I will use the formula mgh, okay, as in my numerators. Okay, so it depends on what form of energy, what time of energy the question question is talking about. Okay, so this is MGH. Okay, so it depends on the question context. So sometimes energy can be found using work done. Okay, and as a result, okay, I will actually use work done formula, okay, given the context, as my to calculate my energy. Okay, so it literally depends on the context and the question that is given to you. But in general, power formula is what we call rate of work energy conversion. Okay, so for example, I have a kettle of 1850 watts. Okay, so which means that looking at this interpretation, I am actually able to give a rough ideal estimation is that in 1 second, okay, 1850 joules of energy is actually being consumed, actually being converted to do a particular task. Okay, in this case, it will be the kettle, it will be electrical energy is being converted to thermal energy to heat up the water. Okay, so this is what we mean by the ideal situation. Okay, but the watts is in terms of energy used per second. Okay, so for in this question, the context here we are looking at for is 1 hour. Okay, so same thing, basic conversion, students you know. Okay, 1 hour is 60 minutes. Okay, so 1 minute is 60 seconds. Okay, so if you put these two together, 1 hour will be how many seconds? 1 hour will be literally equal to 3600 seconds. Okay, so this is the common conversion that we are always dealing with when we look at power. So for 1 hour, the timing that we're looking at for, remember it must be in seconds. Okay, energy, okay, is what the question is asking. Okay, power given in watt. Okay, rearrange the formula using simple algebra, you'll find that the energy given will be 6.6 megajoules, or 6.6 times 10 to the power of 6. Okay, remember, unit answer must be in SI units. It must be in 2 or 3 SF. Okay, unit will be in SI unit for energy will be in joules. Okay, so this is relatively straightforward. Okay, same thing. Here we have a additional thing. We have, for this question, we have a component say 40% of the energy is being lost. Okay, for the electrical motor. Okay, so then we have question asking for useful energy. 40% energy is being lost. So what does this mean in general? Okay, so if you look at conservation of energy, okay, so we have energy input, okay, equal to energy output. This is a simple conservation of energy. Whatever you input, it will be equal to output. But it's just that in this case, the output actually has two categories. One we will classify as useful. Okay, then the other component will be what we call energy loss. Okay, so the energy input, the electrical energy that we are looking out for, okay, actually is being converted to two components: useful energy and heat loss to it could be environment or it could be due to the system. So in this case here, you'll find that based on the question, if I have input, if I classify input as 100%, okay, 60% of the energy used will be actually useful, okay, to do for the washing machine task to do certain rotations, and among this, the remaining 40% is actually being lost. Okay, as well heat and sound, based on the question, heat and sound. Okay, so this is what we mean by the question. Okay, so when we talk about 1.0 kilowatts, 1000 watt, 1 kilowatt, what are we actually exactly talking about? Okay, in this case, what we are effectively looking at is, okay, the amount input that I actually contribute, or the machine contributed, the electrical energy that is contributed to the washing machine is actually 1000 watts. Okay, and out of this 1000 watts, 60% of it actually goes to doing useful work, and the remaining 40% is lost. So if you do a simple math, if my 100% is 1000 watts, 60% will be literally 600 watts, and the remaining 40%, which is 400 watt, okay, will actually be lost to the environment. In this case, remember, conservation of energy still take place. Okay, it's just that now one form of energy, electrical energy, is converted to another form of energy. Not just one form, but two forms. One could be the useful, the other one could be heat loss, and it could be sound energy. So it's more than two forms 1000 joules is being used, electrical energy is being used, and the useful energy consumed is actually 60 joules, followed by 400 joules is being wasted as heat and sound. Okay, so if you look at it, okay, in terms of the working, okay, this is what the students need to understand: the usefulness, the idea of useful energy, and the idea of heat loss. And primarily all these concepts wrap around one single key concept, which is conservation of energy. Okay, so now to complete the question, okay, so to do a simple math, okay, to complete the question, so if we are clear about the question, so now we look at solving it, okay, solving the particular question. With this understanding, okay, we actually can look at how much energy is being lost in 30 minutes. So in 30 minutes, oh, I can't really see it, okay, give me a minute. Okay, so in 30 minutes, the amount of energy being used here, remember the question asks for two things: one is in 30 minutes, and the other one we are looking at is useful energy, okay, in half an hour. So in 30 minutes, half an hour, we are actually literally looking at 1800 seconds. Okay, and based on the question, or based on our understanding, in 1 second 600 joules are being used. It's converted for useful energy. So in 1 second, okay, if I use 600 joules, so 1800 seconds later, how much energy is being used? So this will be a simple rate ratio conversion. So it will be 1008 seconds multiplied by 600 joules. Okay, so the answer here you will have would be a simple, okay, 108, okay, 000 joules, okay, or what we call 1.08 megajoules. This will be the energy that is being consumed as useful energy. Okay, it's quite easily done, but the important thing is to arrive at this working, students need to understand what or how conservation of energy and is being applied. Okay, useful energy and heat loss. Okay. Okay, with this we will come to the end of power. So like I mentioned before, power in this topic is really a small topic. It's quite easily managed. Okay, but the important thing is the usage of the formula, some of the key hurdle. Okay, to use power, I repeat again, the energy that we're looking out for versus the time. Okay, divided by the time. Okay, because units for power is in watts, energy will be in SI units, time has to be in seconds. Most often students will actually forget to convert time to seconds. They will just use whatever units the question actually is given. So as long as the question gives minute, the student will use minute in the formula, and this will result in calculation error. Okay, so other than that, the only thing that I advise students is to, other than be careful of the units, actually read the question carefully. Maybe the question makes certain reference to useful energy, or maybe heat loss to the environment, so it's necessary to get the correct references, okay, the correct context. Okay, that's which is the end of the day that students you will need to read the question carefully. Okay, with this I will go through some of the questions that you need to do. Okay, and before I show you the answers, or before I run through with you, please spend some time on the 3 videos, and after that try out the worksheet that is given to you.